Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, I would like to finish going through the examples of Chapter 8.2, Solving Initial Value Problems with Laplace Transforms. In our last video, we introduced the Laplace transform and solved our first differential equation. I'd like to continue with our guided lecture notes on page 17 with our next initial value problem. Now, to solve our initial value problem, I need you to recall the two formulas we introduced for the Laplace transform of derivatives of functions. And so if we scroll back in our notes, we developed these two formulas for the Laplace transform of y prime and the Laplace transform of y double prime. Now recall our method was to apply the Laplace transform to both sides of our equation, use the linearity properties to rewrite the left-hand side, and then substitute our definitions for Laplace of y prime and y double prime. So let's work on our next example. So here we apply the Laplace transform to the left-hand side of our differential equation. And the right-hand side. And because it's a linear transformation that preserves vector addition and scalar multiplication, the left-hand side can be written as Laplace of y double prime plus 3 times the Laplace of y prime plus 2 times the Laplace of y. And the right-hand side, we'll look this value up in our table of Laplace transforms. So the Laplace of e to the negative 3t. I'm going to scroll back to our table of Laplace transforms. There we go. Remember the Laplace of e to the at is 1 over s minus a. So whatever our exponent a is, it's s minus a in our denominator. So here, since a is a negative 3, the Laplace of e to the negative 3t is 1 over s plus 3. Now let's use our definitions to replace the Laplace of y prime and the Laplace of y double prime. So here, the Laplace of y double prime was s squared times the Laplace of y minus s times y of 0 minus y prime of 0. Where you'll notice y of 0 and y prime of 0 are both given by our initial value problem. So we'll make our substitutions. S squared Laplace of y. Now since y of 0 is 0, this term goes away. And y prime of 0 is 1, so we'll have minus 1. Similarly, the Laplace of y prime. Now our definition was s Laplace of y minus y of 0. But again, since y of 0 is 0, this term goes away. So we get just s Laplace of y. Now let's complete our substitutions. We'll replace s squared Laplace of y minus 1 for the Laplace of y double prime, and s Laplace of y for the Laplace of y prime. So here we'll have s squared Laplace of y minus 1 plus 3 times s Laplace of y plus 2 times the Laplace of y, and this has to equal to 1 over s plus 3. Now, what I would like to do is isolate all of the terms involving Laplace of y on the left side of our equation, which is this term, don't forget to include the factor of 3, and this term. And then the factors that, or the terms that don't have the Laplace of y, will move to the right-hand side of our equation. Forgot the Laplace, L. And so I'm going to move now this minus 1 to the right hand side. It'll turn to a positive 1. And I'd like to be able to combine the two terms on the right hand side. And so let's get a common denominator by multiplying our second term by s plus 3 over s plus 3. So now on the left hand side, let's factor out our common term of the Laplace of y. And on the right hand side, since our two terms now have a common denominator, we can add those together. Now note 1 over s plus 3 plus s plus 3 over s plus 3, I believe, is going to be s plus 4 over s plus 3. And now to get Laplace of y by itself, we'll divide both sides by our quadratic. Now, if this is Laplace of y, then we can say the solution to our dE can be given by y of t will be the inverse Laplace of s plus 4 over s plus 3 s squared plus 3s plus 2. So now we have to recall how to find the inverse Laplace of this function. And again, you probably want to notice here that the denominator is factorable. problem will contain distinct linear factors. So let's apply the method of partial fraction decomposition to rewrite our fraction as distinct linear factors. There's three different terms. So here we would like to write s plus 4 over, now if we factor our denominator completely, I think we'll have s plus 3 times s plus 2 times s plus 1. And we would like to write that as some constant over our first linear factor, some other constant over our second linear factor, and again some third constant over our last linear factor. Now recall, we will decide to multiply everything by our lowest common denominator to clear our fractions. And so we'll get s plus 4 equals a times s plus 2, s plus 1, b times s plus 3 and s plus 1, and c times s plus 3, s plus 2. Now let's choose s to be a number that will reduce the number of terms on the right-hand side of our equation. So here I'm going to let s equal -3. Now if s equals -3, then the left side of our equation becomes just 1. And if s is -3, then this factor will be 0, and so this whole term will be 0. And this factor will be 0, and so this whole term will be 0. So we only have just our first term. Now if s is -3, then we have 1 equals a. Now if s is -3, then we have -3 plus 2 is -1. And if s is -3, s plus 1 is going to be -2. This gives us the equation 1 equals 2a, which tells us a has to be a half. Similarly, if we let s equal -2, now if we let s equal -2, we're going to reduce the number of terms on the right-hand side of our equation. If s is -2, this term and hence, or this factor and hence this whole term goes to 0. And this factor and hence this whole term goes to 0. So we just get left with our middle term. Now if s equals -2, the left-hand side becomes 2 equals b times, now if s is -2, this factor becomes 1. If s is -2, this factor becomes -1. And this gives us the equation 2 is equal to -b, so that b has to be -2. Lastly, let's let s equal -1. Now notice that if s is negative 1, then on our right-hand side, this factor and hence this term goes to 0. This factor and hence this whole term goes to 0. And we're left with just our last term. So if s is negative 1, the left-hand side will become 3 equals c times, if s is negative 1, s plus 3 is 2. And if s is negative 1, s plus 2 becomes 1. Which gives us the equation 3 is equal to 2c. And so that c is equal to 3/2. This now allows us to write our solution y of t as the inverse Laplace of 1/2 over s plus 3 minus 2 over s plus 2 plus 3/2 over s plus 1. Now, since the inverse Laplace transform preserves vector addition and scalar multiplication, we can write this as 1/2 inverse Laplace of 1 over s plus 3 minus 2 inverse Laplace of 1 over s plus 2 plus 3/2 inverse Laplace of 1 over s plus 1. Which will give us 1/2. Now recall the inverse Laplace of 1 over s plus 3 is e to the negative 3t. And the inverse Laplace of 1 over s plus 2 is e to the negative 2t. And lastly, the inverse Laplace of 1 over s plus 1 is e to the negative t. And this is our solution using the Laplace transform. Okay, I hope this is helpful. And our method becomes a little more clear after you see a couple more examples. Let's try another one. And I'd like to give you a moment to work on this one on your own. So maybe this is where you could pause the video and work the Laplace transform, use the Laplace transform to solve this second order linear non-homogeneous initial value problem. And maybe after you get finished, or if you get stuck, come back and we'll see how you did. So I'll see you in a moment. Okay, I hope you paused the video and gave this example a fair try. Let's see how you did. Now what we would like to do is apply the Laplace transform to both sides of our differential equation. Using the fact that the Laplace transform preserves vector addition and scalar multiplication, we can rewrite the left-hand side and the right-hand side. We need to know what is the Laplace of sine of t. So if you have your Laplace table, let's look at the Laplace table. Recall the Laplace of sine of t, so the sine function. Here we have just sine of 1t, so b is a 1. Will end up being 1 over s squared plus 1. So here we're going to have 1 over s squared plus 1. where we can substitute the Laplace of y double prime. Now recall our definition for Laplace of y double prime was s squared Laplace of y minus s times y of 0, your initial condition, minus y prime of 0. Now from our initial conditions though, we know that y of 0 is 0. So this term goes away. And y prime of 0 is 1. So we'll write this as s squared Laplace of y minus 1. Now we didn't have a Laplace of y prime in this example, so the only substitution we make is for Laplace of y double prime. So let's evaluate this, or plug this in for our Laplace of y double prime term. So we'll have s squared Laplace of y minus 1 plus 4 times Laplace of y, and this will equal 1 over s squared plus 1. Now we would like to get all of the terms involving the Laplace of y, which is this one and this one, on the left-hand side of our equation. So we'll have s squared Laplace of y plus 4 times the Laplace of y. And this constant term that doesn't have a Laplace of y, let's move that to the right-hand side of our equal sign to give us 1 over s squared plus 1 plus 1. Now on the left side, let's factor out our common term of Laplace of y, our common factor, to leave s squared plus 4 times Laplace of y. And on the right hand side, I'd like to have a single term. So let's get a common denominator by multiplying this 1 by s squared plus 1 over s squared plus 1. And so that we can make the right hand side be a single fraction as, I think it'll be s squared plus 2 over s squared plus 1. Now we want to get Laplace of y by itself, so we'll divide both sides and write the Laplace of y is equal to s squared plus 2 over s squared plus 1 times s squared plus 4. And if this is the Laplace of y, then our solution y of t has to be the inverse Laplace of this right hand side. So now this is our goal, is figure out what is the inverse Laplace transform of this fraction. And I think what you want to notice here is the right hand side is factorable as distinct irreducible quadratic terms or quadratic factors. So they're distinct irreducible quadratic factors. So this is not like our previous examples where we had linear factors. And if you don't recall how to use partial fraction decomposition when you have irreducible quadratic factors, you may want to look that up on YouTube to remind yourself of this process. I will show you with this example, but you may want to review some additional resources to remember this technique. So here we go. Let's look at your partial fractions technique. When you have irreducible quadratic factors. So here now our goal is to rewrite the fraction s squared plus 2 over s squared plus 1 s squared plus 4. And when you have irreducible quadratic factors in your denominator, your numerator is going to be of the form as plus b. It has to be a linear term in our numerator over s squared plus 1 plus another linear term cs plus d over its quadratic factor. Now we're still going to multiply by our lowest common denominator to clear our fractions, which will reduce to s squared plus 2 equals as plus b times s squared plus 4 and cs plus d times s squared plus 1. Now the problem with these quadratic factors is we cannot choose a single number for s that'll make any of the terms on the right hand side disappear. So with these quadratic factors, our goal is going to be to multiply the right hand side out so we can compare term by term to the left side of our equation. So let's FOIL and rewrite the right hand side by distributing the as to each term, and then we'll also distribute the b to each term. So we'll have as cubed plus 4as plus bs squared plus 4b Similarly, let's multiply the cs and then also the d to get cs cubed plus cs plus ds squared plus d. And now what we would like to do is rewrite the right hand side by combining similar terms together. So what we'll look at is first the terms that contain an s cubed, these two. Let's regroup these and factor out the common factor of s cubed. This will give us a plus c s cubed. And now let's get the terms that have an s squared, so these two, and then we'll regroup them, factor out the common factor of s squared, Similarly, let's grab the ones that have an s, this one and this one, regroup these together, factor out the common factor of s, And then lastly, get our two constant terms, which will be this one and this d, to give us 4b plus d. And somehow the right-hand side has to equal s plus squared. Now there's lots of variations of how this could proceed, but technically what we have is a system of 4 equations and 4 variables here. And you can write your system different ways, but in the end, what you want to be able to do is compare coefficients of each similar type term. So for example, I can say the coefficient of s cubed has to match the coefficient of s cubed on the left-hand side. But there is no s cubed. So technically we should say that a plus c has to equal 0. Similarly, the coefficient of s squared has to match the coefficient of s squared. So somehow b plus d has to equal 1. The coefficient of s on the right-hand side has to match the coefficient of s on the left-hand side, but there is none. So somehow 4a plus c has to equal 0. And lastly, our constant term 4b plus d has to equal 2. So this would be a system of 4 equations and 4 variables. However, this one can be rewritten or also regrouped by identifying that these are the only two that involve a and c. So let's group these two together. And so this tells us, or gives us, just a 2-by-2 system. A plus c has to equal 0, and also 4a plus c has to equal 0. We can solve this system of equations to find what a and c must be. Similarly, this equation tells us b plus d has to be 1, and this one tells us 4b plus d has to equal 2. And so these two equations by themselves create a 2-by-2 system for just b and d, telling us that b plus d has to equal 1 and 4b plus d has to equal 2. Now you can solve these two systems using any technique you wish, but I'm going to use the substitution method here. So let's solve our first one. I'm going to rewrite our first equation as c equals negative a, and substitute this value in for our second equation for c, to give 4a minus a has to equal 0, which gives 3a is 0, or a has to be 0. But if a has to be 0, then I think c has to be 0 also. So from our original partial fraction decomposition, we now know a and c are both 0. Now for our second system of equations, I'm going to use the elimination method. And I'm going to choose to make the d variables cancel. So I'm going to multiply our entire first equation by -1 to obtain negative b minus d equals -1, and our second equation, 4b plus d equals 2. So that if we add our two equations together, the d terms will cancel, and we'll get 3b equals 1, or that b has to equal 1/3. And if b is 1/3, let's go figure out what d is now. And I'm going to use this form of our first equation and replace b with 1/3. So this will give us 1/3 plus d is 1, or that d is 2/3. And this now gives us our other two constants we needed. So now let's go back to our original partial fraction decomposition. We have now determined that a and c are both 0. B is 1/3 and D is 2/3. So this now allows us to write our solution for y of t. As the inverse Laplace transform of 1/3 over s squared plus 1 plus 2/3 over s squared plus 2. And using the fact that the Laplace transform and the inverse Laplace transform preserve vector addition and scalar multiplication, we can write this as 1/3 inverse Laplace of 1 over s squared plus 1 and 2/3 inverse Laplace of 1 over s squared plus 2. Now, using our table of Laplace transforms, we want to recognize that 1 over s squared plus 1, the inverse Laplace of this, is going to be the sine of t. So this will give us 1/3 sine of t plus 2/3, and similarly the inverse Laplace of 1 over s squared plus 2 was that plus 2 or plus 4? I think I miswrote that. It should be s squared plus 4 in our denominator. So let's fix that. This is s squared plus 4. And so this has to be the sine of 2t. Okay, and here's your solution to our initial value problem, obtained using Laplace transforms. Okay, I have one more example to do with you. And maybe this is, since this is our last example, you may want to take a shot at doing this one again on your own before I work through it with you. So maybe this is where you might want to pause your video and look at applying the Laplace transforms to this first order linear non-homogeneous differential equation. And I'll see you back here in a moment after you have a second to work on it on your own. Okay, I hope you paused the video and gave this a try. Let's see how we did. So here, let's first apply the Laplace transform to both sides of our differential equation. And using the fact that the Laplace transform preserves vector addition, we can write the left side as the Laplace of y prime plus the Laplace of y. And the right-hand side, the Laplace of e to the negative t, we should recognize now as 1 over s plus 1. Now, the Laplace of y prime. Let's come up with a substitution for this term. Now, the Laplace of y prime we have as s times the Laplace of y minus y evaluated at 0, where y evaluated at 0 is given by our initial conditions. So we'll make our substitution. S Laplace of y. Now we're minusing y of 0, which is a negative 1, so we get plus 1. And this is going to be our substitution that we put in for Laplace of y prime in our differential equation. So here we'll have s times the Laplace of y plus 1 plus the Laplace of y has to equal to 1 over s plus 1. Now let's obtain or isolate all of the terms involving the Laplace of y, which is this one and this one, on the left-hand side. And then our term, the plus 1 that does not have a Laplace of y, let's move that to the right-hand side. So minus 1. Now on the left-hand side, let's factor out our common factor of the Laplace of y. And on the right-hand side, let's combine our two terms together by getting a common denominator, which means we'll multiply the second one by s plus 1 over s plus 1. So we can combine our two terms together, and I think we'll get negative s over s plus 1. And we want to get the Laplace of y by itself, so let's divide both sides by s plus 1 to give us negative s over s plus 1 squared, which will give our solution to our differential equation y of t as the inverse Laplace of s over s plus 1 squared. Where I think here we want to recognize that our denominator has repeated linear factors. And so you might want to recall how to do partial fraction decomposition. Wait, we don't have partial fraction decomposition here. It's just Well, let's think about how to do this. Maybe there's more than one way we can do this. No, we have to do partial fractions. We do. Okay, so we need to remember how to do partial fraction decomposition when our denominator has repeated linear factors. Okay, let's see how we do this. So let's label first. We'll do our partial fraction technique. Where our goal is to rewrite negative s over s plus 1 squared equals, now remember you might have to review your notes from Calc 2 on how to do complete partial fractions when you have repeated linear factors. But it's going to look like a constant, over s plus 1, so just the first power of your linear factor, plus b over s plus 1 squared. And again, we're going to multiply everything by our lowest common denominator to remove our fractions. And this will give us negative s equals a times s plus 1 plus b. And there's a couple of different techniques you can use to solve for a and b here. But my choice is going to be, like our last example, to multiply the right-hand side out so I can compare coefficients. In which case we'll get negative s, and if I distribute a, we'll get as plus a plus b. And if we now compare coefficients, then the coefficient of s on the right hand side has to match the coefficient of s on the left, which means a has to equal negative 1, and a plus b, your constant term on the right, has to match the constant term on the left, but there is no constant terms on the left, so it has to be 0. So of course this tells us a has to be negative 1, but if a is negative 1, then b has to be positive 1. Which allows us to now write our solution as y of t as the inverse Laplace of negative 1 over our first linear factor s plus 1 plus 1 over both of our linear factors s plus 1 squared. And since the inverse Laplace transform preserves vector addition and scalar multiplication, we can write this as negative 1 times the inverse Laplace of 1 over s plus 1 plus the inverse Laplace of 1 over s plus 1 squared. Now, reviewing your table of Laplace transforms, the Laplace of 1 over s plus 1, well, that's e to the negative t. and the inverse Laplace of 1 over s plus 1 squared. There's different ways you can obtain this from your Laplace table, but you should come up with t e to the negative t. So I'm going to write our solution as y of t equals negative e to the negative t plus t e to the negative t. This is the solution to our differential equation. And this completes the last example I wanted to do with you for Chapter 8.2. This should give you everything you need for completing your homework for Chapter 8.2. I hope this is helpful, and I'll see you next time.